The topic of this lab report is constant velocity. Constant velocity means when an object in motion moving in a straight line at a constant speed over a given time period. The main purpose of this lab is to record and analyze the motion of an object to determine the object position moving at a constant velocity over a given period of time. I then use Newton's second law to create a computational model with Python, and then compare the data from the computational model to my observed data using position over time. Newton's first law of motion states that an object that is at rest will remain at rest. An object that is in motion will remain in motion unless acted by another unbalanced force. If the object in motion does not have any force upon it, that object is at constant velocity. Newton's second law of motion, also known as the momentum principle, focuses on the behavior of objects when the existing forces are not balanced, and states that the motion of an object is dependent upon the net force acting on the object and the mass of the object. The common formula that shows this is F equals ma, where F net represents the total force, m equals the mass, and a equals the acceleration. A deviation of this formula, however, is where v final equals the v initial plus the F net divided by the mass times delta t. When F net equals 0, the object moves at a constant velocity, and when there is no friction within the system, an object with initial velocity and applied momentum will remain in the direction forever. This slide represents the setup for my lab where I used a mini basketball in constant motion. I calculate the mass and diameter of the basketball, as well as the initial position, which is moving in the positive x direction. To calculate the initial velocity, I use the average velocity formula, which is position 2 minus position 1 over the second time interval minus the first time interval. I then recorded the final observed time as well as the mark frame, which is 60 frames per second. When using the tracker application, I set the coordinate plane centered at the center of this ball in this beginning frame here. And I also set the diameter of the ball at the length reference, as shown by the blue segment here. The video in the top right showcases the movement of the basketball in the positive x direction at a constant velocity. The center of the ball was marked at each frame point to measure the position over time, which is then used to calculate the velocity. The graph on the left showcases this data points for position over time, and as you can tell from the straight slope of the line, the object is moving in constant velocity. The video was trimmed due to the ball accelerating and decelerating at the beginning and end of the video. The slope of the curve is not completely accurate because of motion in the z direction as well as friction, which will be explained later. This is the glow script code that I used to create my theoretical model. To begin, I stated the mass of the ball as shown here, and I stated the initial position and the initial velocity as shown here, calculated using the average velocity formula. I then set the delta t, which is the change of time, equal to the frame per second, which is 60 frames per second. From here, I stated the last observed time variable to end the loop, and I made sure the net was equal to 0. I used Newton's second law to update the ball velocity and the ball position, and then used this code to update the time. This is what the code looks like after it is run. As you can see here, you can see the ball moving in the x direction at a constant velocity. This slide shows the results of the glow script code that I created. The remaining data points were calculated using the continuous iteration or loop of velocity update formula and the position update formula until the wall statement condition was reached. This is a computational model, so the data shows the results that we were expected to achieve within the motion of the basketball analyzed by the tracker. So over here, I have the data plot points. I have the position versus time graph, which shows the constant velocity, and I have the velocity versus time graph, which shows the constant velocity in the positive x direction. The graph containing the observed data point and the computational predicted data point is shown on the left side of the screen. When comparing the two models, the slope of the two lines were nearly identical towards the beginning of the motion, but towards the end of the motion, the observed motion from the tracker began to drift away from the computational model data plot. The R coefficient of the basketball motion in tracker is 0.9975, which is almost identical to the R coefficient of the computational model, showing how close they were. The only difference between the slope is by a value of 0.0463. The two reasons why there was a difference between the two data plots is because there may have been some imprecision when determining the center of the ball in each frame when using the tracker application. In addition, the computational model does not take into account friction force, which would have led to a non-zero net force. If the motion of the basketball went in the opposite direction, or if the orientation of the x-axis flipped, the speed of the ball will remain the same since the speed is a scalar, meaning the direction is not incorporated in the magnitude of the speed. But the velocity of the basketball would not remain the same due to the change in direction. Velocity is a vector, meaning the velocity is made up of the magnitude of how fast the ball is going as well as the direction the ball is moving in. If the axis was to flip, the ball that was once moving to the right would now move in the negative x direction, creating a negative slope in the negative y direction, as shown in the graph right here. As you can see, compared to the regular data plot, the new data plot creates a reflection of the original data plot. net force is set to zero within the computational data, the results between the observed and computational model are really similar. Because we know that the object moves with a constant velocity, we know that there is no net force. However, it is not possible to determine all the individual forces that are acting on the basketball. There are so many forces present within the universe, so it is impossible to figure out the number of pushes and pulls that are being applied to create a net force of zero. In conclusion, I learned how to utilize Newton's second law to analyze the motion of a basketball in the positive x direction using track theory, and compare that model to a computational model created on GlowScript.